Video bouncing? Yeah, all right. Dear Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Thank you for the break just completed. Help us to just glorify you in what we do this morning, Lord. In your name I pray. Amen. Okay, guys, so I'll take your homework questions for a little while here, and then I've probably got more calculations to show you. But at least to start with, let's look at your homework questions. So tomorrow I collect homework 8, is it? Right, which is basically everything up through 12.6. But there, of course, are more questions from 12.6 in the next homework assignment. So I'm not saying I'm collecting all of the 12.6 homework, obviously, but you notice I cut it in half in the course planner, right? So just the most basic 12.6 things is what I'm collecting. Excuse me. Yes, sir. 12.5, number 33. So you're asked to estimate the error in the 80th partial sum of the alternating p equals 1/2 series. Did I get that right? Estimate S80 error is that a k plus 1 or? Oh. Oh, okay. You could also write this the sum. You could write this the sum, say n equals 1 to infinity of minus 1 to the n plus 1 over the square root of n if you wanted. And then maybe it's more obvious that it's just an alternating p equals 1/2 series. I mean, it is the alternating p equals 1/2 series. Okay, so it doesn't really ask you to prove that it converges, does it? But I would just say observe it's converging, right? Observe that the b sub k here is 1 over the square root of k plus 1, right? Which is what? Positive. Decreasing. And what? B sub k goes to 0, right? Hence, the series so I'm talking about a problem. I mean, I'm just adding something to the solution. Is not really required for this problem, but I think it's worth saying while we're here. So that series converges by the alternating series test, right? And we also learned that the error, right, if you look at the difference between the 80th partial sum and the series, which I should have given a name by now because this is a pain to write. Oh well. That is what? That is less than or equal to b sub 81. This is the alternating series estimation theorem. It says that the error in the 80th partial sum is at most the next term that you would add or subtract. So you just got to calculate that. I mean, what is that? Is that? Oh, yeah, sorry, 82. Thank you. You are correct, sir. Yes, you are. Does that make sense? I mean, okay. Is that square with what's in the answer key, or? I mean, this is number 33, so. Yeah, this is the alternating series estimation test, which is, you know, there's an error estimation based on the integral test, and then there's this one. I don't think I've clearly stated the integral test estimation theorem just yet in here. and odds of me doing it today are pretty slim. Let's see here. Yeah, well, which are we? Which section are we in? 12.6, 12.5, 33, right? 0.11, 1104. Oh, it's the square root of 80. Oh, okay. So this is like approximately 1/9, which is about 0.11. Yeah. Okay. Yeah. That's consistent with the decimal in the book. Yeah. 18 on 12.6. Okay. Let's look at that. Estimate the maximum possible error if the seventh Taylor polynomial at -2 is used to estimate f of -2. Assume f is a function that has the nth the nth derivative bounded by 1. So it could be like a sine or a cosine, all right? But more generically, it could be some kind of linear combinations of sines and cosines or something. Anyway, it's a function. It's kind of a little bit mysterious. Number 18, was it? So let's talk about this. So you've got you're given f of x, let's say smooth. In other words, you can differentiate it where the nth derivative at x, the absolute value of that is less than or equal to 1 for all x, right? This is given. So like he says, like sine or cosine would be an example of this sort of phenomena. The question then is to estimate the maximum possible error if p of 7 equals to p of 7 at -2 is used to estimate f of -2. You're saying p sub 7 of -2 estimates f of -2. What's max error? Now, in order to understand this question, we have to understand the section. In this section, the Taylor polynomials are their Maclaurin, basically. They're partial sums of the Maclaurin series. So like this p7 of first of all, p7 of x is what? Yeah, f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2 x squared plus and so forth and so on all the way until you get to the 7th, right? Well, I'm not going to write 7 primes there. 7 of 0 x to the 7th, right? That's the 7th Taylor polynomial at x. What happens when that is an approximation to f of x, right? This plus some remainder, in this case the 7th remainder of x, is approximately, well, that's not approximately, this is just equal to f of x. And then as 7 goes to infinity, sorry, we don't usually say that, but all right, anyway. So what's p sub 7 of -2? What is that? These questions are not disconnected. In fact, the question being asked number 33 before this question was really nice. It was a nice setup for what we're doing here. Let me show you why. This is what? This is like f of 0 plus what? Plus f prime of 0 minus 2. And I think I'm also told that the derivative Well, I'd like to assume that f is positive and that its derivatives are positive. I'll show you why. Otherwise, I'm not sure what to do. Maybe you guys can tell me. F prime prime of 0. This is time, right? Yes, thank you. So let me just, right, and then two to the what, 7th, right? And then what, plus the reason this wouldn't be P of, this is P7 of minus 2, right? So what I'm suggesting is we can say f of x is equal to, I'll get to it eventually. F of x is equal to the sum k equals 0 to infinity of the kth derivative at minus 2 divided by k factorial times 2 to the k times what? Minus 1 to the k. What I'm trying to say is f of x you could think of as being an alternating series, but the thing that gives me pause is what if the derivatives of f were negative? I don't know. I'm not sure what to do here unless I know that all of the derivatives, the function, its first, its second, its third, the 7th derivative, they're all positive. Let's just assume that for a second, okay? If I do make that assumption, and so forth and so on, actually, all right? Greater than 0. You can solve the homework problem under this assumption, okay? I'm adding that to the problem for your convenience and for my sanity today. Excuse me. I'll crack open the solution here in a second and see if the book has something more to say, but this is definitely one way we could solve it. So if we know that these derivatives are positive, then what is that up there? We call this thing S. Then S is an alternating series with b sub k equals to what? Well, it's the kth derivative evaluated at minus 2 divided by k factorial, which is, by the way, positive, decreasing, and has limit 0, assuming that we know that the arbitrary derivatives are bounded between plus and minus 1, right? I'm not sure what to do if the values of the derivatives are negative. I'd have to come up with an alternative argument for that contingency, but if this is the case, if I do know the derivatives are all positive, then it's an alternating series. This is the kth term, right? It goes to 0. So that is a convergent alternating series which models the function at 2. And what's the error in P7? It's just P8 of minus 2, right? So what is it? Oh. You guys don't look like you trust me. I better not put down that screen just yet. this problem is very abstract in a certain sense, right? Like, there's this function f. We don't know what it is. We just know that its derivatives are bounded between what? They have a magnitude at most 1, right? And do we have anything else to work with here? I don't think so. This one was problem, what was it, section 12 point what? 12.6. All right, let me consult the master. Let's see here. Or the master's henchman. I'm not sure who wrote this really. Come on. Number 33, right? Oh, goodness gracious. What's wrong with me? Yes. So the textbook, the solution in the textbook is literally it's a line, and it assumes that f of minus 2 is written as an alternating series. Is there some way to, I mean, maybe my intuition just isn't good enough. If the derivative was possibly positive, could you, is there some reason that if I guess if some of the, I'm trying to think of how would you compare the Taylor series to, like, let me just write it down. How would you compare? Maybe there's a reason that we don't need to know the derivatives are all positive. How would you compare this versus this? See, because this series, I mean, and there's, of course, there's also what? Minus 1 to the k. I guess we don't need that. I mean, fine, 2 to the k. See, this would be the series formed from looking at the absolute values of the derivatives. So, like, if I look at the series on the right, then I can definitely apply the alternating series estimation theorem to the one on the right, right? That is a series of positive terms. Is that related to the other series in some sort of nice way? Oh yeah, it is, right? So I'm just missing a stupid idea. I mean, a kind of obvious but silly idea, which is that well, oh, excuse me. I don't know. There's just something I can't. There's a reason that you can conceptually assume that the values of the derivatives are positive here and not lose anything. I think. I'll try to think about it some more and see if I can put it in better words later. Let me go on to the other homework problems. I mean, this is the solution to this one. That actually is. What is this, by the way? This is what? We take the 8th derivative, evaluate it minus 2, divide by 8 factorial, right? And then multiply by what? By 2 to the 8th. That's not, I'm sorry, it's not, golly, it's not P8. That's not the right thing to write here. What should I write here? This is not correct. It's not even S8. It's B8, right? It's I should have B8 here, quote unquote. Right, where B8 is this. And I'm sorry, I still have this wrong. Oh, you guys gotta bring me back in here. What am I missing on my B? Come on, guys. I'm studying this series, right? What's part of it? Not just the f prime, not just the kth derivative divided by k factorial. There's also this piece, right? So I should have a 2 to the k. part of that, right? That doesn't, I mean, still, is it decreasing? It's k factorial, right? K factorial beats 2 to the k upstairs. We know that. So it is decreasing. It does go to 0. Nothing I said was wrong. It's just incomplete, yeah. Okay, so I would say that there's some short argument that I am close to understanding but not quite able to communicate to you guys that says I can compare this series to that series, so this one will be, let's say, possibly further away from the truth, so it doesn't have a smaller error than this one. And so if I find the error in this, then I've also found the error in that, at least an upper bound on it. But this one, this guy on the right, that actually basically allows me to assume that my b sub k is what? The kth derivative evaluated at minus 2, the absolute value of that, divided by k factorial times 2 to the k, right? And that, folks, given that the kth derivative is bounded by 1, definitely goes to 0 and satisfies the criteria for the alternating series test, right? You see, I mean, I hope you guys understand what I'm doing. I'm just trying to apply the alternating series test to the series which the Taylor's theorem generates for us, right? Make sense? I'm going to shut up. Are there other questions? 12.4, number 22. Oh no. I guess now is as good a time as any to talk about. Uh-oh. Gotta find an eraser that's not going to work against me. Questionable. Maybe. Let me hazard a picture here. I'm not sure what's the best way, but let me start from the middle. You're given a series, right? Let's say sum over a sub k. What do you, and you're asked, does it converge or diverge? What do you think about here? Some things I think about, kth term test, right? I think about, is it geometric, right? What else do you think about as a first line of attack? Maybe, is it a p-series, right? What's another first line of attack? Is it alternating, right? What else is at the first line? Does it look telescoping? Is there anything else that's on the first line of defense? Geometric, kth term, is it a p-series? What else is there? What other tests don't require a lot of effort? They just kind of require looking at it and going, oh, wait a minute, it's that kind of example. I need to go from there. I think that's all that comes to mind right off. Past this is what, though? Past that, then you've got things that require a little bit more effort, right? Like, can I compare it to p-series, right? And there you kind of got two directions. You can either do limit comparison Or you can do direct comparison or basic comparison, as he calls it, right? Those are one direction you can go. Past that, what's the other thing you can do? Kind of in another direction, you can try root test, right? Or you could try ratio test, right? You could also have things like, and related to this, sorry, can I compare to something that is nice for the integral test, right? And again, you can either do limit comparison or you can do basic comparison for one of those, right? Something that's nice for the integral test would be something like, for example, the sum n e to the minus n squared, right? Something that you know how to, you look at it and go, oh, use substitution, right? And maybe your series is kind of like that, but not exactly that. But maybe you could compare to that, you know? Let's see here. Is there anything else that belongs on this hideous chart? There's kind of a more basic, let's say, triage I do on the problem, which happens back here really at my initial thinking, which is what? Think about intuitively. For large k, right? A sub k is approximately what? I really feed that intuitive guess into this web of thinking. All right, so like, for example, you know, if I've got something like sum of root k over plus k to the 7th divided by k to the 18th plus 2, then I go, oh, well, this is really just the way, I mean, this is really just like focus on the dominant pieces, this and that for large k. So this is approximately 1 over, you know, this is approximately the same as 1 over like k to the 11th, right? So this is really more or less a p equals 11 series. That's the kind of calculation which makes me go down these red paths, right? Or something that would guide me over to this would be something like I had something like sum n plus 3 times e to the minus n squared plus 7 or something like that, you know? I might look at that and go, well, that's kind of like n times e to the minus n squared. Maybe I can compare to that because I know that converges by integral test. These are things I might think. All right, so let me get back to your question finally. I wanted to take a couple minutes to try to at least take a stab at explaining sort of our general web of logic. I mean, you try to do the easier tests first, right? Now, of course, the ultimate egg in my face would be if I try to do this problem and I can't do it according to my web of thinking. And that may be the case for this one. You've got k factorial squared divided by what? 2k parentheses factorial and indeterminate starting point. We can put k equals to 0 there just for the sake of specificity. All right. Which one was that? That was number 22. Okay. Section 12.6 was it? 12.4. All right. Yeah. Now I would add to my picture. Maybe you can correct my picture and join to it the logic of the paragraph on page 596. Right. You should definitely, as you were mentioning, Thomas, look at page 596. Nice advice there, right? It's hard to capture everything I'm trying to do with some simple heuristic or even picture. But page 596, there's some nice advice there. Excuse me. About, as you look at a formula, when can you kind of see when to use root versus ratio or something like that? Now, I look at this, and I think, it feels like ratio test to me. What's that? You did ratio? And it worked? You think it worked? Now, is this one of the ones where the ratio works out to infinity for you? Curses. It brings us back to the question I haven't answered yet. Let's think about this. And your intuition was that the ratio test being infinity should mean it converges. At least other things online say so. Yes? Oh, diverges. Oh, because it's greater than 1. So if that's the case, I should be able to compare this to something that the ratio test works for in the context of our book, right? I should be able to find something larger, no, something smaller that also diverges. Well, certainly you can say k factorial squared over 2k factorial is greater than or equal to, excuse me, k factorial over 2k factorial. That's no help. That's no help. That converges. That's no help. All right, let me just face the music here. Now wait a minute. If you got the ratio test works out to infinity, we ought to be able to show that the kth term goes to not to 0. If I trust you, yes, sir. So I mean, did you also find that the ratio test works out to infinity? Oh, okay. Well, let me just take a calm look at the ratio. Yeah. Let's just work it out here for a second before I'm going to take the advice of the last great American president, which is to trust but verify. Let's see here. So let me check you guys. Oh my goodness, yes. Thank you. The monstrosity of this. All right, so cleaning this up a bit, we've got k plus 1 quantity squared times k factorial quantity squared divided by 2k plus 2 factorial. Upstairs, I've just got 2k, let me say parentheses factorial, divided by k factorial quantity squared. So these cancel. And this down here takes a little work. This is k plus 1 times k plus 1 times 2k factorial. To actually get to 2k factorial, we've got what? We've got 2k plus 2 times 2k plus 1. And then what's left in there is what? The 2k factorial, right? So as I think about expanding this, I have 2k plus 2 times 2k plus 1, and then times 2k minus 1, times 3 times 2 times 1. So what's left is the 2k factorial, right? Now those cancel, and what do you get? Yeah, I'll divide by k squared. I get 1 plus 1 over k, 1 plus 1 over k, and then 2 plus 2 over k, 2 plus 1 over k, which goes to 1 times 1 divided by 2 times 2. I'm sorry, I seem to have solved your problem. converges by ratio test. Ooh, ouch. Yes, that would do it. Whew, well, I feel better. Now I don't have a ratio test at infinity problem anymore. I mean, I'm still curious about what does it mean if the ratio test works out to infinity. My intuition is if that is the case, we should also be able to show it diverges by the kth term test. And it should probably be manifestly so, like in our face, kth term test goes not to zero in such a case. I think we can go back to that. The proof of all of our divergent cases, every theorem we've proved in here in the divergent case, if it's like a multi-part theorem, what was the nuts and bolts of the proof of in the divergence case? It was always use the kth term test, right? It's always that. So as a generic fallback, if we have something we think is divergent, you can always fall back on the kth term test and try to see why the kth term is not going to zero. Wait a minute. Well, I guess that's not entirely true. I do have divergent series which don't have the kth term going to not zero, right? I mean, like the harmonic series has kth term going to zero, and yet it's divergent. So what I'm saying isn't quite said right yet. What I'm trying to say is there are a lot of divergent series which have kth term not going to zero. Those ones are easier to argue the divergence of. Stuff like the harmonic series, well, that's the subtle part. Things that have the kth term going to zero, and yet they diverge. So, anyway, you guys have other questions? 22 and 12.6, okay. By the way, a specific example for this, like this number 18, maybe I should really just take a minute and say, for example, to build off number 18, if we had like f of x equals to, say, sine of x, right? Then f prime of x would be what? Cosine of x, f prime prime, minus sine x, right? And so forth. So when you look at P7 of x, what do you get? You get like x minus 1 over 3 factorial x cubed plus 1 over 5 factorial. And this is what he has in mind when he writes his homework problem, right? He has in mind something like this, really, and so when you plug in minus 2, right? I end up with an alternating series, right? I mean, if you keep going, right? So, like, if I look at this, so I mean, it's part of an alternating series. So just like I told you guys from day one, when we talked about convergence of a series, I could tell that I was close to that sine of 1 because sine of 1 is an alternating series, right? So I can bound the error in the nth sum by the next one. That's what he has in mind here in number 18, some function like sine, exactly. So like this one, I guess it would be something like that. That would probably give you, this would give you a bound if you plugged in 2. Like the error can't be more than like 2 to the 9th divided by 9 factorial if I use this much to approximate sine of minus 2 with that 7th Taylor polynomial. Number 22, you said? Now we're given that the derivative is less than or equal to 3, and we're supposed to find the least integer n for which you can be sure that Pn of 2 approximate f of 2 within 3 decimal places. Now, again, we're going to assume that the I guess the thing is, if the derivatives of the function are negative, right, then that would be a better thing in terms of it's converging, right? So if some of the derivatives are negative, that means, I think it means it's getting closer to the convergence thing faster, right? To the limit faster. So if I assume that all of the derivatives are positive, that would be like the worst case scenario in terms of not converging to the limit as fast. So if I want to find like a maximum bound on the error, just assume all the derivatives are positive. I think that's roughly the intuition here that we need to operate on, because all right, so basically the same as this one. So we have f of x smooth, and we're, instead of this being 1, it's what now? It's 3. And we're supposed to not estimate 2, right? Piece of n? F of 2. F of 2. Max error. All right. Yeah. Oh, okay, so I guess you have Pn of x is what? The sum k equals 0 to n of the kth derivative evaluated at 0 divided by k factorial times x to the k, right? And so what we have is that f of x is equal to what? Is equal to the Pn of x plus the remainder, the nth remainder of x. And this nth remainder of x goes to 0 as n goes to infinity if the Taylor series actually converges to the function. What we're trying to do is we're looking at f of 2, right, minus Pn of 2, right? So that's the error in nth, Taylor polynomial approximation of f of 2, right? We've been asked to put a max, like a, what's the worst case scenario, given that you know that that this is equal to what? This is, on the other hand, this is what? This is, that's Rn of 2, right? But I suppose, I don't know, I'm kind of beating around the bush here. This is equal to what? I mean, this is equal to, assuming convergence, this is equal to the sum k equals n plus 1 to infinity, right, of the kth derivative at 0 divided by k factorial times 2 to the k, right? That's actually the remainder of the series. We're trying to say how small can that be? for n. Yep.
Should it be a less than sign between like the absolute value of 2 minus p sub n of 2 and then less than o sub n?
No. Because this is an identity, like, so just to give you an example, explicit example, like sine, for example, sine of x, right? I can write, this is just straight up an identity. X minus 1/6 x cubed plus 1 over 120 x to the 5th plus dot, 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 right? So I can actually write sine of x minus x equals to 1/6, well, minus 1/6 x cubed plus 1 over 120 x to the 5th plus dot, dot, dot. Now here, I would be comparing like f of x minus p1 of x, and that's equal to the first remainder of x, for what it's worth. And then, but the problem is we need to say this is less than or equal to something. I mean, that's, now for the alternating series, the remainder is bounded by just the next term. Because if you think about an alternating series, the largest thing it is its first term, right? And then you're subtracting stuff, and then adding smaller stuff, subtracting stuff, adding smaller stuff. So like an alternating series starts out the biggest it's ever going to be. Just like the picture of the n equals half, right? Like you start out at 1, go back to a half, 5/6, but that 1, that first term in the alternating series, is its largest value. So if you look at the tail, the remainder series in an alternating series, well, its first term is its largest value, and that's the alternating series test, is that's the biggest it can be, right? So the question is, how do you, we know that this is what? This is less than or equal to, I guess we can look at this. Excuse me. There's probably n plus 1, infinity. The kth, now what do we know about the kth derivative at 0 for this problem? We know that that is at worst, what's the worst case scenario? 3, right? That was given in the problem statement, right? So I could say this is less than or equal to 3 over k factorial times 2 to the k. Oh. Cool. Oh, I can actually do this one. I don't know if I'm supposed to be able to do it that way, though. I'm just going to show you. I can actually calculate this exactly. Is that what I'm supposed to do? Just a second. Let me look at the man behind the curtain here for a second. You know, just because I can do something doesn't mean I should do it with you guys. Let's see here. Which problem are we in? 22? You guys should make me look at this to start with. Oh my goodness. All right, well, he says that he basically assumes it's an alternating series again. He says it's less than or equal to the next term. So he seems to be claiming that really? Well, that just doesn't seem fair. There's something I'm missing here, guys. Sorry. This is what we get for not proving things.
I don't know if this has anything to do with it, but we are just looking for like accuracy to the third decimal place, not the max error.
Oh. That is useful.
I mean, could you not set r sub n to equal or less than or equal to, say, 0, 1, 1, 0, 0, 0, 1?
Yeah. I mean, that is what we want, right. Of course, yes, thank you guys. N is not given. We're trying to find n such that this is less than 0.0. What do you say, how many places? You want it to be accurate to 3 decimal places? In my book, that means you put I don't know, I mean, that's debatable. Do you put 0.001 here, or do you put, I guess 1? That means that, I guess, yeah, that should give you accuracy to 3. That means that the last digit could be at most 1 plus or minus 1 in the last digit, right? Like, so if you get if you work out the nth partial sum and it's 3.456, then it could be between 3.457 and 3.455. Like the last digit could go plus or minus 1. Is that what's meant by certainty to 3 decimal places? Seems to me like you might want this, right? That means that the 3rd decimal place is certain, and that the variability is only in the 4th decimal place. That's personally what I would want. If I want 3 certain decimal places, I would actually put 0.00. I think he might. Of course, that may be too greedy, right? You could do what? How about this? 5. That would be right on the cusp of things, because that way, right? Let's see here. So if you want 1.132 to be certain, right? That means that if I have a 6 over here, in my calculation, I would have been to what? Like 133, right? If I had a 4 here, I would go to 132. So if I'm calculating things to 4 decimal places and I want my round off to be correct, I need to know that last thing within that much, right? Otherwise, I could round wrong. It's something like that. I mean, the question is, what you want the error to be small enough so that the first 3 decimal places in your approximation are legit. So if we make the error less than 0.005, that will do it, in short. If you just start thinking about details of rounding, I still think logically there's some exceptional cases you could still go wrong, but they're like statistically, it becomes a question of statistics in some sense here. Like I said, if you put 0.0001, which is greedier, then I would just, without much thinking, I'm sure that I've got the first 3 decimal places. In fact, I even know something about the 4th decimal place if I put 0.001 here, 3 zeros and a 1. Now, let me just look at his example for a second. Maybe we can understand what on earth it is that I'm missing today. I'll leave this here. I don't want to draw it again. So most of his examples are I understand the alternating examples. I understand, right? Alternating examples, fine, great, easy. Alternating series test, right? How is he understanding the estimation of error in non-alternating examples? That's the thing I don't think I've communicated to you guys worth a bit yet. His example 6 is such a thing. Let's try to work through this. Maybe we can salvage whatever. And what I'm not telling you is something just like not that complicated. So e to the 0.2 to what? 3 decimal places is what we want. So we're trying to approximate the exponential to 3 decimal places using the Maclaurin series, I think. So he says, okay, so Pn of 0.2 is equal to 1 plus 0.2 plus 1/2 0.2 squared plus 1 over 3 factorial 0.2 cubed plus plus 1 over n factorial 0.2 to the n, right? Why is this? Because we know that e to the x is equal to a sum k equals 0 to infinity of x to the k over k factorial, right? So this is this is the nth. This is exactly just, so like if I look at the nth Taylor polynomial centered at 0, I just have this, right? And if you plug in x equals to 0.2, we get that. I hope you guys understand that much. I hope the error is harder, right? So here's what he does. He says we know from example 3 that the nth Taylor polynomial for e to the x, he says we know from example 3 that the remainder of 0.2 is less than or equal to, oh, you know what it is, guys. Oh man, I was kidding a little bit earlier when I said this is what we get when we don't prove things. But actually this is exactly the problem. We haven't proved Taylor's theorem. The Lagrange's error estimate is what we need. Duh. Oh goodness gracious, guys. I'm an idiot. So he's got e to the, where is this coming from? E to the 0, this magical factor here. E to the 0.2 times 0.2 to the n plus 1 divided by n plus 1 factorial. Hmm. 610. Yeah, the previous thing, 605 perhaps.
I mean, I think the e to the 0.2 is like the largest term in the whole series of polynomials. That's why it's there.
Well, let's see here. Let me follow the logic here for just a second. So this is less than e to the 0.2 to the n plus 1, fine. And then what? He trades the e for a... So he then rewrites this as... And this is just being lazy, basically. 3 over 5 to the n plus 1. That you could leave the 3 as an e there if you want, guys. That's not mission critical. To 3 decimal places, and then so again, if you want the 3 decimal places, what the book says is basically if you bound the error by 0.005, and you notice that this is already larger than the real error as given to us. By the way, this is also an upper bound on the real error. This is by Lagrange's estimation, Lagrange's error estimation theorem. Let me state that here. Which, by the way, is what we need to prove that Taylor's series converges and junk. If you said 605. Yeah, Lagrange's formula for the remainder says that Lagrange's formula for remainder. It's kind of a juiced version of the mean value theorem or something. I don't know. So the magnitude of the remainder of x is less than or equal to the absolute value of the nth derivative at some value c times, what is it, divided by n factorial, n plus 1 factorial, times the absolute value of x to the... Now, I added some absolute values to this, okay? It's got no absolute values in the book because it's actually a formula for the remainder precisely. So for something like this, what is f of x? F of x is equal to e to the x, right? So what's f prime? What's the nth derivative of x? We talked about this the other day. Well, it's just e to the x again, right?